Welcome back to the next class of theory of computation. In this class, we are going to look at another example on language specification using context-free grammar. Here, we would be writing a context-free grammar to generate a language L equals to 0 power m, 1 power n, 0 power m plus n such that m and n are greater than equals to 1. This means we would be writing a context-free grammar that would generate a language that consists of all the strings that have m number of zeros followed by n number of ones, which is again followed by m plus n number of zeros, right? And the value of m and n should be greater than equal to 1. That means the minimum string that would be accepted by this particular language should be 0, 1, 0, 0. The other strings that would be generated by this particular language would be of the form 0, 0, 1 followed by 3, 0. This means there are 2 zeros, so m is 2, 1, 1, that is n is 1, so it should be followed by m plus n zeros, that is 3 zeros. Similarly, the other string in this language can be 0, 1, 1, 1 followed by 4 zeros, that is 0, 0, 0, 0 and so on. So all the string would follow the pattern, that is m number of zeros followed by n number of ones, which is again followed by m plus n number of zeros, right? So to generate such string, we would be writing a production that would add a 0 at the start and an equivalent 0 would be added at the end, right? So the number of zeros that is required at the start, those many number of zeros would be added at the end of the string, right? And this production can be repeated any number of times as the number of zeros, that is m number of times. Once the number of zeros at the start are added, then we should be able to add a 1 in between, that is after zeros, and a equivalent 0 at the end for this 1. So we can add the 0 equivalent to this one in between, right? So as soon as the number of zeros are done, we should be able to produce an equal number of 1 and zeros. So 1 at the start and a 0 after that 1, right? So we need to write production in such a way. So the production that we would be writing would be as follows. First, we would be writing a production that would add a 0 at the start and a 0 at the end. But this can be repeated any number of time. But as soon as zeros are done, we should not be able to again put a 0 in between, right? Because as soon as you reach a 1, then you should go to 0 and there should be no other 0 at the start. That should be the second part of the string, right? So for that we use a new non-terminal over here, 0a0, right? Then this a should now produce any number of zeros at the start and the end. So we again write a rule 0a0. So by using this rule, we can repeat any number of zeros at the start and the equivalent number of zeros at the end. Now we want that in between there should be 1 followed by equal number of zeros, right? So this a should now be able to produce a 1 after this 0 and a 0 at the end. So we add a production such that it would add a 1 at the start and a 0 at the end. So we add 1b0, that would be used to repeat the number of ones, and or 10 if there is a single 1 in between, right? Similarly, we would be writing a production for b so that we would be able to repeat the number of ones in between. So we write a rule as b derives to 1b0, and to terminate this b we would be writing 10. As the number of m and n should be greater than equals to 1, we won't be using epsilon over here, right? So this particular set of production rule would generate the language 0 power m, 1 power n, 0 power m plus n such that the value of m and n is greater than equal to 1. The grammar for this would be represented as g equals to set of non-terminals as SAB, set of terminals as 0, 1, set of production rule P represented by this set of productions, and S as the start symbol. Right. Now consider a string 0, 1, 0, 0. This would be generated by the given set of production rule as follows. We will start with the start symbol, use the production 0a0. After this 0a0, there is 1 directly. So we would be using the production 1 0, a d raised to 1 0 here, and then we would be getting the required string as 0 1 0 0. So consider another string 0 1 1 1 0 0 0 0, right? So this is one number of zeros followed by three ones, and then it is followed by four zeros, right? To generate this, we would again be starting with the start symbol of the grammar, and s derives to 0, a0 is the first derivation, and as the number of zeros are already achieved, we would be moving to 1. So we would be replacing this a with the production that would generate a 1 after the first 0, and that is a derives to 1b0. So we would be replacing this a with 1b0. Then we want there should be three ones, so one is already generated, so we would be again repeating the same production so as to add the second one. So we would get two ones now and a 3 0 at the end, right? So 0 2 ones and then 3 zeros at the end, and now we want that there should be a last one and equivalent 0 at the end, so we would be using the production b derives to 1 0. So we, in this way, we generate the required string, right? And this by using this set of production rules which are given. So in this way we can generate all the strings that follow the pattern 0 power m, 1 power n, 0 power m plus n, such that m and n are greater than equals to 1 by using the given set of production rules. Thank you.